Hello friends, I welcome you in lecture number 5 on series solutions of differential equations. In lecture number 4, we have discussed about power series method for finding series solution near an ordinary point. In this lecture, we will discuss one question about finding power series solution of differential equation near an ordinary point. This question was asked in GTU Summer 2019 exam for 7 marks. So we discussed this question. Find a power series solution of the differential equation y double dash minus xy equal to 0 near an ordinary point x equal to 0. This differential equation is known as Airy's equation. So we will see how to obtain power series solution of this differential equation. Now first we show that x equal to 0 is an ordinary point of this differential equation, and for that we compare this differential equation with this standard form y double dash plus px y dash plus qx y equal to 0, and we can see coefficient of y dash is px and there is no y dash here, that means px equal to 0, and coefficient of y is qx which is minus x here, and we have px equal to 0 which is a constant polynomial, qx equal to minus x is also a polynomial, and we know that polynomials are analytic at every point. Therefore px and qx are analytic at x equal to 0, and hence x equal to 0 is an ordinary point of this differential equation. Here it is given that find power series solution near an ordinary point x equal to 0. That means you are given that x equal to 0 is an ordinary point. So if you are not showing this part, then also it is fine. You can directly start with the power series method. Now we know that if x equal to x0 is ordinary point, then equation has power series solution in powers of x minus x0. We have discussed this power series method in lecture number 4, and we know that if x0 is an ordinary point, then differential equation always have power series solution in this form an times x minus x0 raised to n. Here x0 is 0, therefore differential equation has power series solution y equal to sigma an times x raised to n. Here we take x0 equal to 0, and we will have an times x raised to n. N is from 0 to infinity. Therefore we have written that therefore there exists a power series solution of given equation 1, which is in this form y equal to sigma n equal to 0 to infinity an x raised to n, and in this solution these an's are unknown. So our aim is to decide these unknown coefficients an, and differential equation is of second order, so we require first and second derivatives of this function y. So if we differentiate with respect to x, we will have y dash equal to sigma n equal to 1 to infinity this an as it is, derivative of x raised to n is n times x raised to n minus 1, and second derivative is sigma n equal to 2 to infinity n an as it is, and derivative of x raised to n minus 1 is n minus 1 times x raised to n minus 2. Now y is solution of this equation, therefore y must satisfy this equation. That means we can substitute values of y double dash and y in this form. We will put y double dash and y in given equation. So in the next step we write that putting values of y double dash and y in given equation is y double dash minus xy equal to 0. We write y double dash equal to this summation n equal to 2 to infinity n minus 1 an times x raised to n minus 2 minus x times y. Y is sigma an x raised to n equal to 0 to infinity. In the next step, I keep this summation as it is, and I can take this x inside this summation because this x is independent of this summation index n. Here summation index is n and x is independent of n, so we can take it inside the summation, and we will have x raised to n times x, that we can write as x raised to n plus 1. Now next step is, first we will rewrite these two summations in such a way that power of x is x raised to n. So for that, here for the first summation, here power of x is n minus 2. So here we, for the first summation, we take n minus 2 equal to say m. Therefore n will be equal to m plus 2. So we are changing summation index from n to new summation index m by this substitution, n minus 2 equal to m. So if I take n minus 2 equal to m, n will be equal to m plus 2, and n minus 1 will be equal to m plus 2 minus 1, that is m plus 1. And here range of n is from 2 to infinity. So if I take n equal to 2, m will be 0. So m will start from 0. And here n is from 2 to infinity. So m will be from 0 to infinity. So using this, we can write this summation sigma n equal to 2 to infinity n times n minus 1 a n x raised to n minus 2 is equal to new summation, new index is m, and range of m is from 0 to infinity. N is m plus 2, n minus 1 is m plus 1, a suffix n, n is m plus 2, and x raised to m. Here I have to write properly, this is m. So I am converting, this is from n minus 2 to mth power. Now we know that this index m is dummy index. So if I wish, I can write, instead of m, I can write n also, because all these n and m are dummy index. So I can write this by replacing m by n. So I am writing by replacing m by n, and I have converted my summation into nth power of x. Here power of x is not n, so I am converting it into nth power. Same thing we will do for this. Here also we will take n plus 1 equal to some another index. Suppose I consider n plus 1 equal to say s. Therefore n equal to s minus 1, and n is starting from 0. So if I take n equal to 0, s will start from 1. So s is from 1 to infinity. N plus 1 is replaced by s, and n is replaced by s minus 1. So now we write this summation an x raised to n plus 1 sigma an x raised to n plus 1, n is from 0 to infinity. This we are converting in terms of s. S is from 1 to infinity. A suffix n, n is s minus 1, and n plus 1 is s. And because this s is dummy index, we can replace s by n also. So n is from 1 to infinity, a suffix n minus 1 x raised to n. So I have converted this summation from x raised to n plus 1 to x raised to n. So all these things you can do as a rough work, and if you wish you can show them also in your answer. And after converting this I am replacing this n equal to 2 to infinity. This summation is replaced by this sigma n equal to 0 to infinity n plus 2 n plus 1 an plus 2 x raised to n, and this second summation is replaced by this one, and I put them here and I obtain this equation. So first step is we will convert all the powers of x in terms of x raised to n. After putting values of y, y dash and y double dash in given equation, we will write all the powers of x as x raised to n by converting in this way. If I am not having nth power, I will assume that power equal to say m or s as I need, and then I will be able to write summations in such a way that I have nth power of x. That is my first modification of this equation. Okay, fine. So I have converted those two summations such that I obtain x raised to n. Now I can combine two summations if range of index is same. Here n is starting from 0 to infinity, here n is starting from 1 to infinity. So what I will do is I will write this as this summation sigma n equal to 0 to infinity as term corresponding to n equal to 0 plus sigma n equal to 1 to infinity. So first I will take n equal to 0 and I will write down the term corresponding to n equal to 0. If I take n equal to 0, I will have 2 here, here I will have 1, here I will have a2, and x raised to 0 is 1, and plus this summation but n starting from 1 to infinity, because here n is starting from 1 to infinity. So I am taking term corresponding to n equal to 0 outside, or as in the addition. So here for n equal to 0 I have 2 into 1 into a2 into x raised to 0, that is 1, plus sigma n equal to 1 to infinity n plus 2 n plus 1 an plus 2 x raised to n, and I keep this as it is because here I have summation from n equal to 1 to infinity. Now because these two summations are from 1 to infinity, we can use this logic. We know that if I have sigma an minus sigma bn, if range is same, n equal to 1 to infinity, n equal to 1 to infinity, then this I can write as sigma an minus bn, n equal to 1 to infinity, provided all these summations or series are convergent. So now we combine these two summations and we will have sigma n equal to 1 to infinity, this quantity minus this quantity, and x raised to n can be taken common. So in the next step we are doing that procedure here. We write this is equal to sigma this minus sigma this equal to sigma n equal to 1 to infinity n plus 2 n plus 1 an plus 2 x raised to n minus an minus 1 x raised to n, and we take x raised to n common. So now you can see I have written my left hand side in this form. We can see that I have constant term 2a2. If I take n equal to 1, I will have some quantity into x. If I take n equal to 2 here, I will have some quantity into x square, and so on, that is equal to 0, which I can write as 0 plus 0x plus 0x square. So this is possible if and only if all these quantities, that is coefficients of x and constant term 2a2, this quantity, all these coefficients are 0. That means this equation is satisfied if and only if 2a2 equal to 0 and this coefficient of x raised to n equal to 0. So in the next step we consider that equating the coefficient of each power of x to 0 we get 2a2 equal to 0, that means a2 equal to 0, and n plus 2, n plus 1, an plus 2 minus an minus 1 equal to 0, and here summation is from 1 to infinity, so this is for n greater than or equal to 1, or we can write n can take the values 1, 2, 3 and so on. And from this I find that an plus 2 equal to 1 over n plus 1 n plus 2 into an minus 1, n equal to 1, 2, 3 and so on. So this is the recurrence relation, and this is very important. Recurrence relation, and using this recurrence relation we will be able to decide all these coefficients an. So now we can find out particular constants for particular values of n. We can find for few of the values of n by taking particular values. For example, if I take n equal to 1, I will have left hand side equal to a suffix 1 plus 2, that is a3. For n equal to 1, this is going to be 2, and for n equal to 1, this is 3, and for n equal to 1, this is a0. So for n equal to 1, I will obtain a3 equal to 1 divided by 2 into 3 into a0. For time being, I keep this as it is. I am not writing 1 over 6 into a0. So in the next step, we take n equal to 2. So if I take n equal to 2, I will have a suffix 4. This is 2 plus 1, that is 3. This is 2 plus 2 into 4. And for n equal to 2, I will have a1. For n equal to 3, I obtain a3 plus 2, that is a5. If I take n equal to 3, I have 4 and into 5. For n equal to 3, this is a2. And we have obtained that a2 equal to 0. So this is 0. So a5 becomes 0 because a2 is in the product and a2 is 0. Then we consider n equal to 4. So for n equal to 4, we have a6 equal to n is 4. So 4 plus 1 5, 4 plus 2 6, n is 4. So we have a3, and a3 is 1 over 2 into 3 into a0. So if we put value of a3 here, we have 1 over 2 into 3 into 5 into 6 into a0. So we obtain a6 in terms of a0. Then we take n equal to 5, and we find that for n equal to 5, left hand side is a7, and here for n equal to 5, I have 6 and 7 and a4, and a4 is obtained here. It is 1 divided by 3 4 into a1. So if we substitute value of a4, we obtain a7 equal to 1 divided by 3 4 6 7 into a1. Similarly, I have obtained for n equal to 6, I obtain a8 equal to a5 times this, but a5 is 0, so a suffix 8 is 0. For n equal to 7, I obtain a9 equal to 1 over 8 into 9 into a6, and then I substitute value of a6 here, and I write a9 in terms of a0. And for n equal to 8, I write a10, and a10 is a7 into 1 over 9 into 10. a7 is already obtained. It is 1 over 3 4 6 7 a1. So we substitute value of a7 and we obtain a10 in terms of a1. So I have find particular these ans for particular values of n, and I find that every constant is converted in terms of these two constants, a0 and a1. All the constants are in terms of a0 and a1. So you should find sum of the constants. If you are getting some constants 0, then you should try for more values of n. Here I find that a2 is 0 and a5 is 0. So I am obtaining values of ans for n up to n equal to 10. Now once we obtain values of ans, we can recall that our solution is in this form: sigma an x raised to n equal to 0 to infinity, and we have to substitute values of an. So that series solution I have written the terms up to x raised to 10, a0 plus a1x plus a2x square and so on, and then I substitute values of all these constants: a0 as it is, a1x as it is, a2 is 0, similarly a5 is also 0 and a8 is also 0. a3 is a0 over 2 into 3 x cube, then a4 is a1 over 3 4. So I am putting values of these constants: a3, a4, a5, a6, a7, a8, a9 up to a10. So I substitute all those values here and I find this type of series solution up to the terms containing x raised to 10. In the next step, I combine all those terms which contain a0. All these terms are containing a0. So we can take a0 common, and if we take a0 common, we will have 1 plus 1 over 2 3 into x cube plus 1 over 2 3 5 6 into x raised to 6 plus 1 over 2 3 5 6 8 9 into x raised to 9. So I obtain a0 into this series which contains these powers: x raised to 3, x raised to 6, x raised to 9 and so on. Similarly, I take a1 common. If I take a1 common, I will have x in the bracket, I will have x, then x raised to 4 by 3 into 4, then x raised to 7 by 3 4 6 7, x raised to 10 divided by 3 4 6 7 9 10 and so on. So you should at least try to write first 3 non-zero terms for each of this series. I have written up to first 4 non-zero terms, but it is advisable that you should write at least first 3 non-zero terms for each of this series, and for that you should try to find out this for particular values of n from the recurrence relation. You should try to obtain values of an so that you can write your power series solution in this form. So finally our power series solution is in this form: y equal to a0 into some power series in powers of x plus a1 into another power series solution in powers of x. So this is the general solution of given equation. We know that if I have second order ordinary linear differential equation, then its solution is in this form: c1 into y1 plus c2 into y2, where y1 and y2 are linearly independent solutions. So that matches here. c1 and c2 are a0 and a1, and y1 is this first series, y2 is given by this second series. So it is easy to obtain the series solution. You should just remember all these important steps. First step which we started is we assume that y equal to sigma an x raised to n equal to 0 to infinity is solution of given equation, and then we find out y dash and y double dash. After that we substitute values of y double dash and y in given equation, and then in the next step we first try to make power of x as n. We will find out those summations in which power of x is not n. Here we have two summations, and in both the summations power of x is not n. So by converting or by transforming this summation index, we are able to convert these summations in powers of x raised to n. After that we will try to make the summation starting value of summation as same, or we will try to make the range of summation index same. Here this is starting from n equal to 0 to infinity, this is from n equal to 1 to infinity. So first I am writing this as something plus summation from n equal to 1 to infinity, so that I can combine these summations whose range for summation index is same. Here both the summations are from n equal to 1 to infinity, so that we can combine them. So that is the another important step. And once you are able to do this, you have to equate all the coefficients of x raised to n to 0, and you will be able to obtain the recurrence relation like this. This will be different in different differential equations, and from this recurrence relation try to obtain some values of these ans by taking particular values of n, and after that you substitute all these values in this solution, and after that you try to write down your solution in this form. So finally your solution must have only two constants or arbitrary constants. Here a0 and a1 are arbitrary constants. All other constants are converted in terms of a0 and a1. So this is all about power series method. It is very easy, but you should take care while you are writing all these things. You should take care of your calculations. So this is all about this session. Thanks for watching.